All right, and hi everybody, as we get set for a look at the power rule for derivatives, and this is going to learn to save us a whole lot of time. So let's start out with something pretty easy. We've got the function f of x is equal to 3, and if we think about what the graph of this function looks like, we probably already know. It's kind of like saying y is equal to 3. So the graph of that particular function, y is equal to 3. As you can see, I'm doing a little sketch here. That's going to produce a horizontal line just like that y is equal to 3. So the question here is, if a tangent line were drawn to any value of x, what would the slope of that tangent line be? Well, if you draw a tangent line, it's just going to pretty much be horizontal as well. So it's probably safe to say that this tangent line would have a slope of 0. So based on this process, if f of x is some constant, then the derivative of any constant is going to be 0. Okay, doesn't matter what it is. If your function is negative 12, then the derivative of that function will be 0. If your function is just pi times e, for example, two of our favorite numbers, well, they're both constants, and that derivative works out to be 0. You get the idea. Derivative of 0 should be 0. But what about when we have different types of polynomial functions? So what I'm going to do here is I'm going to do the derivative of each function. I'm just going to tell you how the movie ends when we run it through the limit process. And then let's see if you can figure out what we're trying to come up with for a rule here. Okay, so we've got this first function. This is a quadratic, and it's 3x squared minus 2x plus 3. Its derivative, once we run it through the limit process, f prime of x, that works out to be 6x minus 2. Okay, so now we've got this next one, which is negative 5x to the third plus 2x squared minus 3x plus 1. That derivative works out to be negative 15x squared plus 4x minus 3. Okay, pretty good so far. All right, so now what we need to do is we need to keep going here, and we've got another function. Its derivative is going to be negative 9x squared plus 24x to the third. And maybe by this point you're starting to get the idea of what it might look like. For this next one, negative exponents. Not a big fan, as you well know, but we could work around this, not a problem. It's going to be, let's see, it's going to be 2x to the negative second. Well, that's going to be a minus, actually. Minus 6x to the negative third. Now, we don't like negative exponents. So if it's okay with you, I'm just going to take a quick step and simplify that into 2 over x squared minus 6 over x to the third. And you see we've even got fractional exponents here. So what does that look like? Well, let's figure the derivative here. Let's see, that's going to be, I got to make sure I don't say too much here, otherwise I'm giving the store away. 4x to the negative 1/3 minus 8x to the negative third. And again, we're not a fan of that. So we'll just go ahead and move those downstairs. A lot of students ask me, they say, well, Mr. Winter, I know that x to the 1/3, I know that's equal to the cube root of x. How do you want it? How do you want your answer? Do you want it in fractional power, or do you want the radical? And my response is either one is acceptable as long as it means mathematically the same thing. So I don't care which one you use, it's fine. All right, now let's go to this last one here, and we've got f prime of x will be 3x to the negative 3/2 plus 3/2 x to the -1/2. And again, I'm just going to go ahead and clean that up a little bit. I mean, honestly, we're really not testing on rules of exponents here, although a good knowledge of them helps. So 3/x to the 3/2 and 3/2x to the 1/2. All right, so now I've done all those derivatives, and you kind of see what the result is when it's all said and done. Now would be a good time to maybe pause the video for just a moment and think carefully about how you would complete the rule if I've got some term that's being raised to a power. How would I deal with that? Pause the video right now. Okay, so now that you're back on live with me, let's go ahead and tell you what the power rule is. The power rule is going to be n times x to the n minus 1. So basically what we're going to do here is we're going to take whatever the power is, bring it down in front as a coefficient, and then drop the power by 1. So let's go back up and look at some of these examples here, and you'll see what I mean. Just a couple that I want to run through here. So this first one, 2 times 3 for 6. Drop the power from 2 to 1. The power here was 1, so 1 times 2 is just going to be 2. And if I drop the power down to 1, that's going to be x to the 0 power, and anything raised to the 0 power is just 1. So there's really no need to write it there because it's like multiplying by 1. It's pretty boring. Okay, and then this constant drops out like we talked about on the previous slide. Okay, so we'll run through down here with this example, the fourth one. -1 times -2, positive 2. Then I drop the power by 1. -2 times 3 is -6. Then I drop the power by 1. And it even works just as cleanly for these two down here. So 2/3 times 6 is 4. I take away 1. 2/3 minus 1 is -1/3. And then I go ahead and have -2 times 4 for -8. Then I drop the power by 1 down to -3. Okay, so basically that's what we're dealing with here, is the idea that you take the power, bring it on down, and then lower the power by 1. A very important point that I need to add on to help you understand the power rule is any fractional powers are easier to differentiate than radicals. And move anything downstairs to the upstairs if possible, with a negative exponent. Okay, so that's a couple of things that we can do to make our life a little bit easier. We can convert any radicals into fractional powers, and anything that's in a denominator, let's move it upstairs and give it a negative power. Okay, now a couple things that are kind of like, it's almost kind of obvious what we're doing here, but I feel the need to just kind of let you know that they're there. One of the principles that we covered with limits was something called a constant multiple rule. And that constant multiple rule is something we've already kind of been using here. If I have a constant times something with u, then it's going to be that constant times the derivative of whatever u is. Okay, so what does that mean in terms of like a power rule situation? Well, what it means is I'm going to take this power, I'm going to bring it down and multiply it by whatever's in front, and then I'm going to drop the power by 1 in my derivative. Okay, so we've kind of seen this a little bit at work here. Now I'm going to go ahead and give you the quick version here of how you can handle a radical. Once again, let's change it into something that's easier to work with. Let's be really, really super selfish here to make this a lot easier. So a power of 1/2 is equivalent to a square root, so that's why I rewrote it as 2x to the 1/2. And if I want to find the derivative of that function, dy over dx, I'm going to take the power, multiply by what's in front. 1/2 times 2 is just going to give me 1. And then I'm going to take that power and lower it by 1. Okay. Now lastly, we're going to put everything back together again and get rid of all the negative exponents. So I'm just going to move that downstairs. 1 over x to the 1/2 or 1 over root x, whichever you prefer as your choice. Okay. All right, let's go to this one. Now, I want to point out that when it comes to the fractional powers should be 2/3. So what I have here is 1 over 2x to the 2/3. When I move this up, I'm going to leave the 2 down there because it stays. But the x to the 2/3, I can move that up to ground level and give it a negative power. Okay. So now when I go to find the derivative of this function, it's now in a much better, much easier to deal with format. So I've got negative 2/3 times 1/2. And then I lower the power by 1. So if I drop that power by 1, it's going to be negative 5/3. So I'm taking away 3/3 from this already. Okay, now let's do a little cleanup on aisle 1 here, and I'm going to get negative 1/3 x to the negative 5/3, also known as negative 1 over 3x to the 5/3, and this is your derivative right here. All right, last one, and I think you're going to find this one is a lot easier to handle. When we have negative 3x over 2, we can just simply write it as negative 3/2 times x. They mean the same thing. And then when I go to find dy over dx, well, the power on this guy is just 1, so we're going to multiply it by the negative 3/2. We're going to drop the power down to 0, but once again, anything that is raised to the 0 power, that's equal to 1. So we really don't need to write it there. The derivative of that one is just negative 3/2. Okay, pretty easy to handle. Nothing too serious here so far. What we have also been doing, kind of secretly on those examples on the previous page, were some examples involving the sum and difference rules. And that is, if we've got 2 or more functions that are being added together or subtracted in that order, then I just can take their derivatives in order. It's sort of like a term-by-term derivative thing and follow the signs. So if I'm taking the derivative of u plus or minus v, then it's going to be u prime plus or minus v prime, or if you like that Leibniz notation, du over dx plus or minus dv over dx. These two mean the same thing. There's really no distinction between what they mean. They're the same. Because once again, we're running into a scenario where they like to have several different ways to say the same thing. And sometimes that can be really annoying, and sometimes it can be really easy to understand. Okay, so if I have a function big F, and it's f plus g minus h, then big F prime is going to be little f prime plus little g prime minus little h prime. Just going to follow the same signs as I had in between those two. Pretty easy. Okay, so for our last little part of this video, let's go to the top of this page and let's talk about the sum and difference rule. And I'm pretty sure that you can give these a shot on your own, and I want you to go ahead and try them very quickly, and then we will come back with answers on all 3 of these in just a short time. So please pause the video at this point and try them for yourself before you come back to this. Okay, so we zoomed in on this one a little bit, and it's going to be pretty easy to do. 4 times x to the 3rd power, and then just the minus 5, and then this constant of 8 disappears when you do the derivative. So that shouldn't have been too bad. Let's move over to part B. And when we see part B, we notice that we've got really negative 1/2 x to the 4th plus 3x to the 3rd minus 2x. So power times the coefficient to get -2, drop the power. Power times the coefficient, drop the power. Power is 1 times the coefficient is just -2, drop the power, and the variable goes. And you've got -2x3 plus 9x squared minus 2. Okay, our last one here today for good discussion is going to be this one right here. Now, before I get going on the derivative, it's probably a really smart move to rewrite this in terms of fractional powers. So this x to the 1/2 is the same as the square root, and then this is going to be 6x to the 1/3, because x to the 1/3 is the same as the cube root of x. Okay, so moving along here, we can finally do the derivative. I take the power, multiply it, and drop the power by 1 to get 1/2 x to the -1/2. So I drop the power, that's going to be -1/2. And then 1/3 times 6 is 2. 1/3 minus 1, -2/3. So a little bit of cleanup on aisle 2, getting those things back downstairs where they belong, those misbehaving children. And you get 1 over x to 1/2 minus 2 over x to the 2/3. Okay, that's a really good intro into the power rule, and I think now you've got an excellent plan for jumping on this with both feet. Good luck.